Here we go. Hi, everyone. Welcome to our final space webinar, the final class that Diego and I are doing together about space in this round of webinars. Oh, woo, woo. All right. I am so excited to talk to all of you about this. We have talked about stars. We've talked about the planets in our solar system. We've talked about what it's going to take to colonize our solar system, about all this other stuff. But there's so much more cool things that happen in our solar system that aren't just the sun and some planets and some moons and stuff like that. So I wanted to go over those last things with you guys.
There's a lot of stuff going on out there.
There's so much happening. April says that she's sad that the grand finale is today. She wishes she had more classes of Delphi. But on the bright side, this is space class. Oh, man, you really need to tune in for the next webinar at 2:30. Just be there. Actually, I know that you're already signed up for it. Okay, good. Evelyn says that she is from the far side of the moon. Welcome from the far side of the moon, 238,000 miles away. Lila says that she saw Venus and Mercury in the sky last night. That's awesome. Venus is a gorgeous, maybe the most amazing thing to see in our sky other than our own moon. It's so bright right after sunset.
Which one's hotter?
What?
Mercury or Venus?
Venus is hotter. Mercury is closer to the sun, but Venus has a thick atmosphere to it, and that traps that heat and turns it into a giant oven.
I would have got that wrong if it wasn't for your solar presentation that I was part of and learning along the way. So as we teach, we learn.
That is so true.
I've learned a lot just getting ready for these and kind of going, okay, I'm making sure I have my facts right and everything.
Yep. Anything that we say to you guys, we really want to make sure we're saying the right thing and we're not giving you information that is incorrect. And I learn stuff every time I prepare for a class, and there's some things in these slides specifically that I learned last night. I was like, oh, I didn't know that. That's really cool. Really cool. Sarah says that she's from Alderaan.
Alderaan.
Oh, I'm so sorry. I'm so sorry. Isis is from Pluto. Neither of those are planets anymore, so you got that in common. And Aubrey's from California. Roundbeer says hello from Kepler 22b. Yes! Someone was at my exoplanets webinar. That's so cool.
That's awesome.
All right. Let us get into the thing that we're going to talk about today. Our solar system, more than just planets. Planets are totally cool, and they're, the most important thing to me because I live on one. But let's learn more. The asteroid belt. I think we've probably all heard of and are somewhat familiar with the asteroid belt. It is the region of space between the orbits of Mars and Jupiter in which most asteroids are located. Here is a shot, a image, a picture. All those green specks are asteroids. Every other mark on there is also some other kind of asteroid or comet or something in our inner solar system.
And the center is the sun, right?
So here's the sun right there in the center. It's that, it's a star. Look, it's actually a yellow little thing in the shape of a star. Whoever made this, I like them very much. Here's the orbit of Mercury.
And I think it's something to point out about a graphic like this is that it looks really dense. And so you would walk away thinking,
what'd you call me?
The graphic looks really dense.
Oh, the graphic.
It looks like there are asteroids just crazy packed in there.
Yeah. But the reality is that this asteroid belt and almost every asteroid belt is nothing like the asteroid belts that you see. And I think of Star Wars first, but I've seen it in a lot of different sci-fi TV shows and movies where you see a ship having to dodge in and out of the asteroids and dodging around, and TIE fighters crashing into stuff. That is not what an asteroid field is like. That's not what an asteroid belt is like. Maybe if it was a brand, two big things crashed into each other in space and started spitting rocks everywhere, that would be like that. Or if you were in the rings around a planet, it might be like that.
Our asteroid belt, not so much.
You could fly through the asteroid belt 1,000,000 times in different directions and never even come close to hitting anything. You wouldn't even come close enough to an asteroid to be able to see it. The challenge of getting to a specific asteroid, just to be able to take pictures of it, is so difficult because stuff is big, but space is bigger. Way
like the way you put that.
Bigger.
Yeah.
Yeah.
There's big things out there, but space is on another level.
Can you look up really quick?
Sure.
What is the distance between here and Neptune in light minutes? How many minutes does it take light to get from Earth to Neptune? We're using Google for this. Google is an amazing resource. If you have a science question, hey, Google, what is the distance in light minutes from Earth to Neptune? There we go. So I think we're all familiar with the fact that when someone is watching us type, we instantly lose the ability to type words correctly.
They have the sun, so sun to Neptune is
about 159.6 light minutes to Neptune. Okay,
yeah.
So Shanna says that she's from Neptune. Please respond. Shanna, I will respond to you in 159 minutes because that's the light delay, at least. Okay, well, the Earth is 8.5 light minutes from the sun, so 159 minus 8.5. So I will reply to you in 150.5 minutes. Oh, I just replied to her. Okay.
And the leg going from Earth to Mars is about 20 minutes.
That's right.
For any other smart Alex out there.
Yeah, that's me. Okay, so here is a picture showing different things that are in the asteroid belt. You can see there's plenty of asteroids within the orbit. So here's Mercury, Venus, Earth, Mars, and then that outer blue line is Jupiter's orbit. And so you can see with the red, there's plenty of asteroids inside of Mars's orbit, but there's way more outside of Mars's orbit on the way to Jupiter. Here's another visual representation of stuff in our solar system. You've got Mercury, Venus, Earth is right there. There's Mars's orbit, that reddish line, and then you can see all those blue bits, those blue dots. And then there is Jupiter. Now you notice there's this blue ring of stuff here, but then there's also like a pink smudge and a lighter pink smudge. What are those? Good question. We're going to learn about those a little bit later.
Cool.
All right. Lorna says, I am from the sun. Respond. I will respond to you in 8.5 minutes when light is able to make that trip. I know. I'm being...
No, this is good. It gives you like the practicality of what these things are going to be like as we explore the solar system.
Yeah. AG. Great question. Do asteroids orbit the sun, or do they just float around? They absolutely orbit the sun. Anything that is not orbiting the sun is going to get pulled into the sun and eaten by the sun, and it would have a long time ago. The sun is a source of gravity. It is pulling stuff into it. It's sucking things in. And the only way to not get sucked into the gravity of the sun is to be moving fast enough sideways relative to the sun that you're falling, but you're falling to the side fast enough that you don't fall in. The same reason, if I were to take
demo kit,
this piece of wood and throw it, it's going to fall and it's going to be drawn in by the Earth's gravity and only travel so far. If I give it some more force, it still falls, but it goes farther. If I were to throw this block at, I forget the velocity needed, but there's a certain speed that I would need to throw it. If I threw it that way, faster than humanly possible, and it was moving fast enough, it would fall down at the same speed, the same rate that the Earth was pulling it down by gravity. So every time it fell down an inch, it was moving around the Earth enough that it never really got closer to the ground, and it would orbit all the way around the Earth. And then after enough time, oh man, it's gone. Anyway, it would come all the way back around and hit me in the back of the head if I didn't turn around and catch it. That's called orbiting. So that's how the Earth is. That's how Venus, Mercury, Mars, and all those asteroids are moving super fast through space, sideways, so that they don't get pulled down into the sun. AG, I'm so glad you're here. Okay. All right. Oh boy, so many comments. So
Like
many
a
comments. So
boomerang,
many
yeah.
comments. All right.
Cool.
So AG asked, so do the asteroids stay in the same position relative to the Earth? No. There's a graphic coming up a little bit later that's going to show that. Thank you for that question. I'm going to pick that up in a little bit. Okay, so that's the asteroid belt. And the asteroid belt is estimated to contain between 1.1 and 1.9 million asteroids larger than 1 kilometer in diameter, and millions of smaller ones. Now, that's not the only belt in our solar system. There's also something called the Kuiper Belt, which we've talked about briefly in some earlier webinars. Kuiper Belt is a region of the solar system beyond the orbit of Neptune, hey Lorna, containing many comets. It's out there, it's like, he didn't pronounce that word right. Many comets, asteroids, and other small bodies made largely of ice. There's so much water. There's so much water ice out in the universe. Here is a picture of all that little stuff on the inside right there. That's the inner 4 planets, Venus, Mercury, Venus, Earth, and Mars. And that little tiny donut in the middle, that's the asteroid belt. Then you've got Jupiter, Saturn, Uranus, Neptune. And then you've got this belt right here. This other second belt out there. And that, a lot of the inner stuff, the asteroids in the asteroid belt, those are made of rock. And there's some iron in there as well, or metal, different metals. This outer stuff is mostly ice. There's some rocky bits in there as well, but there's a lot of ice objects. And when those come in closer to the sun, they turn into comets. They are comets. Then they turn in, they grow their tails in a comet like you are used to seeing. The Kuiper Belt, so far, there are more than 2,000 Kuiper Belt objects, or KBOs for short. KBO, that have been cataloged by observers, but they represent only a tiny fraction of the total number of objects that scientists think are out there. Astronomers estimate that there are hundreds of thousands of objects in the Kuiper Belt region that are at least 60 miles wide or larger. That's a lot.
Yeah.
Tons.
Wow.
The Kuiper Belt is named after this guy, Gerard Kuiper. He lived from 1903 to 1973, and he was what you would call a smart dude.
Smart.
Yeah, look at him. He just looks intelligent. And here he is looking at pictures of space stuff and with books about space behind him. If I were, that looks good. All right.
What amazes me about these guys is how smart they were able to become without the internet.
Without the internet. We could Google the
the
light speed from here to Neptune. He would have to look in a book and do the calculations.
Yeah. You could just the amount of things he had to figure out and read and do firsthand mathematics and do all the accounting for all those things. Just amazing.
So cool. All right. Alette says, I forgot Pluto. I did not forget Pluto. I did not forget Pluto at all. The world forgot Pluto.
And earlier I heard you say a word. I heard you say interstellar.
Interstellar.
Have we talked about what that word means?
Interstellar means between stars, going between stars. And like interplanetary would be between planets, going from one planet to another. Interstellar, the space between stars, going from one star to another. Our first interstellar mission as humanity will, I hope, be in the next kind of 40, 50 years. And I'm sure that the first interstellar mission that humanity sends will be to our closest neighboring star to us. That is called Proxima Centauri. It's about 4.2 light years away from us. It's a long distance.
We need some improved engines.
Yes, we do need improved engines. So Sarah asked, why is Pluto's orbit in a straight yellow line? That is actually not Pluto's orbit. That is, okay, so there is a sign saying, here's Pluto right here. That yellow line is the path of the New Horizons spacecraft, which launched in 2007, 8, something like that. It launched about a decade ago, I think. I am totally not certain on that number. But it launched several years ago, and it traveled out and flew past Pluto and took amazing pictures, incredible pictures, got us the best science. It launched January 19th, 2006. I was close.
Yep.
Good. So it flew past Pluto and took a bunch of pictures and took scientific measurements and stuff like that. So that's why you see that yellow line there, and that's why it points at Pluto.
And it had some bonus science.
Bonus
It
science.
flew by the Snowman asteroid.
Yeah, so it was a comet, and it's called MU-69, and it was able to fly past MU-69 after it passed Pluto, and it took pictures of MU-69 and got a bunch of science about that too. And he called it a snowman because it kind of looked like a snowman.
Yeah, bonus science.
Bonus science. Do you want to visit a snowman?
Yeah.
Excellent.
Very cool.
Now, so you're probably thinking like, that's super far out there. Look, that's way farther out than I thought our solar system went. Guess what? We're not done yet, not even close. There's something beyond the Kuiper Belt called the Oort Cloud. And that is a region of the solar system far beyond the orbit of the dwarf planet Pluto. I like it. A little bit of shade getting thrown right there. The dwarf planet Pluto, in which billions of comets move in nearly circular orbits unless one is pulled into a different orbit by a passing star.
Wow.
So what does this look like?
Nobody said they were from the Oort Cloud. That's good.
I have not mentioned the Oort Cloud at all in any of the prior
Okay.
space classes that we've done on these webinars. And I love the Oort Cloud. I really wanted to talk about it with you guys. See that tiny little yellow ring in there? That tiny little completely insignificant speck on the screen, which if you're watching this on your phone, you might not even see that unless you pinch and zoom in. That's the Kuiper Belt. All the rest of this, there's an inner Oort cloud and an outer Oort cloud, and it looks like a giant bubble. Those are all comets orbiting around our sun in circular orbits, so they stay far away.
Wow. Look at the distance you have.
Look at the distance. This is
100,000 AU, astronomical unit.
So an AU is an astronomical unit, and that is the name that scientists have just made up and given to the distance from the sun to the Earth. It's about 93 million miles. So instead of, if we're still counting miles at this point, the number just gets so big. It's like you wouldn't use inches or you wouldn't use feet to measure the distance from New York to San Francisco. You would want to use miles or something like that. Well, you wouldn't want to use miles to measure these kinds of distances. An AU is a nice, handy, useful unit, 93 million miles-ish. This whole cloud that you're looking at is 100,000 AU across. So that's 93, is that right? Yeah, good. So 93 million times 100,000. Start adding zeros, and you'll get there eventually, okay?
Yeah.
Now, it talked in that definition about how their orbits are going to stay the same in that nice circular stable orbit until and unless something comes by, like another star floating by out there many, many light years from us that just kind of, it's in a nice circular orbit, and then it gets pulled a little bit one direction. Once that other star passes by, now the comet is going to start coming in closer to our sun on a pretty steep orbit. So you can see this long orbit that this comet is going to have. It starts way out there in the Oort cloud, kind of there. That's where it gets pulled by, by gravity, by a passing star or something like that. Or maybe it collides with another comet out there, as statistically unlikely as that might be. And it gets flung into the inner solar system, and it's going to go shooting past and back out to the Oort cloud. And some of these things take millions or billions of years to make that journey, to make that trip. The closer it gets to the sun, the faster and faster it goes, and the more it heats up, and it starts to have this tail appear. I should have put pictures of comets in here.
Yeah. Did you see Halley's Comet when it happened?
No,
Okay.
because if my recollection is correct, the last time that Halley's Comet passed by the Earth was 1986. Is that correct?
Yeah, that sounds right. Yeah, I remember.
That's the year I was born. So
okay. Sorry,
you walked into that one.
Okay, yeah.
So I will have the honor of seeing Halley's Comet when I am 76 years old. because Halley's Comet comes by every 76 years.
I saw Halley's Comet. Woo-hoo.
I was too young. So there's that. Anyway. So it goes faster and faster. It gets
Dab on me.
as it gets towards the inner solar system. And then as it starts to go back out towards the Oort Cloud again, it's going to get slower and slower and slower as it's coming down. I'll move my mouse here. As it's coming down this path, it's getting slower, 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 slower. And finally, it slows so much it stops moving away. It's still moving sideways, but it's moving away slower and slower. And then it turns around and comes back in for another pass at the sun. The Oort Cloud is estimated to have over 2 trillion objects. That's a lot. That's like more than 3. Yeah. Okay, good. Oh, boy, 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 boy. So many comments. I'm sorry that I'm not going to have a chance to read every single comment and question that comes our way. And I do want to warn you guys that we're going to end off just a little bit early today. And the class says it goes through 2:15. I'm going to end off at 2:10. Actually, really end off at 2:10 because we've got just a lot of setup in here to do for the final webinar grand finale that is at 2:30. All right. Shanna asked, how many comets have crashed into the Earth? A lot. Scientists theorize. Their theory is that when the Earth was first forming 4.5 billion years ago, and the solar system was still just a chaos of stuff flying around and floating around and crashing into each other, and Jupiter hadn't even made up its mind how big is it going to be and how hungry is it. That a lot of comets collided with Earth at that time, and that is where we likely got our water from.
Yeah, I wonder how many.
It's a good theory.
How many hit Earth just on a daily basis? It has to be.
Well,
dozens.
Comets.
Or I mean, not a comet. Sorry, not a comet.
We're not getting hit by comets on a daily basis,
Yeah.
but the Earth,
but a meteor.
the Earth is getting hit by little micrometeorites, little tiny asteroids, or sometimes bigger asteroids, every day. In fact, the Earth eats, I think it's 100 tons of material every day.
That sounds about right. When I was younger, I thought, well, if we're sending stuff to space, aren't we going to get rid of all the stuff that's on Earth?
Nah, man.
Reduce our gravity.
Nah, man. The Earth eats a lot of stuff every single day. We just don't even notice it because it's so slight compared to the overall gravity and mass of the Earth. And it's usually so small, it's specks of dust and stuff hitting us all the time, every day. Okay, so Jan Oort is the guy that figured out what the Oort Cloud was, and he made his initial observations and guesses about it. He lived from 1900 to 1992. Shanna's right, she did the math. He lived to be 92 years old. And this looks like a guy who loves his job. Look at that guy. I mean, he's just observing away about the universe.
Ooh, what telescope is he using?
A big one.
Yeah, I wonder where.
Do you know
where he's going?
Earth. Okay. I don't know the answer to your question. Okay. I'll be honest. The entire purpose of me doing this webinar right now is because I wanted to talk about this. I wanted to talk about Lagrange points.
These are cool.
It's so cool to me. Lagrange points are 5 points relative to 2 objects in space where the gravitational pull is balanced. All right, I said some words.
Everybody say the name. Lagrange.
Lagrange points is French.
Lagrange.
Is he French?
Sounds French.
Sounds French to me.
I'll fact check that one.
I don't think he was originally from France. I think he moved to France later in his life. Was he Italian? Let's see if I got this right. I did not look this up yesterday.
It sounds totally French to me.
It sounds super French. So it's 5 points in space relative to 2 different objects where gravity is basically balanced. You're not getting pulled towards one thing or the other. It's just perfect, right? So here is an illustration of the 5 Lagrange points between the Earth and the Sun. And the first, obviously there's going to be a spot right in between, somewhere in the middle between the Sun and the Earth, where you're being pulled equally by the Sun and the Earth. So if you're just sitting there, you're not going to fall towards the Earth or towards the sun. You're just going to kind of park there. That's called the L1 point. The second one, if you go from the sun past the Earth and keep going, then there's a spot further out where you're far enough away, you're not going to be pulled towards the Earth, but you're not going to be pulled towards something else out there either. Again, if you park like a satellite or something like that, a telescope, a space telescope out there, it's just going to sit there in that point in space. If you go from the Earth to the sun and then keep going all the way over to the other side of your orbit, that's called the L3 point. And then to the left and right in the orbit of the smaller object, there's the L4 and L5 points. All right. I hope I'm not going too fast on this. We're going to look at more graphics of this that help illustrate it some more.
I couldn't find anything.
Oh, no. Okay, that's fine.
Yeah.
Aubrey asked, why are we ending at 110? 110. Well, for you, might be 110. 210 for our time here. If I said 110 earlier, it's because I'm talking really fast because I'm so excited. And I drank a lot of coffee. We just need a little bit more extra time between this webinar and the grand finale at 2:30 just to get set up and stuff like that. Okay. I did say 110. All right, the comment section is in. I said 110. I was incorrect. So here's a map that is showing the pull of gravity between the sun and the Earth. So these lines are like how strong is the gravity. Kind of if you were looking at a map that have lines that show different elevations. So obviously there's a point right in between the sun and the Earth, not in the middle of it. It'll be closer to the Earth than the sun, where there's that green dot where it's being equally pulled between the Earth and the sun. So again, if you put a spaceship up there, if you put a satellite, it's just going to sit there. You're not going to use it. Have to use pretty much any fuel to make sure that it doesn't drift away or fall in towards the Earth or something like that. Again, you can see out past Earth, there's that L2 point that is again very stable. L3 on the far side of our orbit. And look at this, L4 and L5 have these big regions, kind of bigger than the Earth itself, where there's kind of a whole neighborhood of space out there where the gravity is kind of not pulling you one way or the other. We're going to look at how that might be in our solar system and what that could mean in our solar system in just a couple of minutes.
And so Lagrange was from, it's a last name.
Okay. Yeah.
It's an English last, it's a French last name.
There we go. Joseph Louis Lagrange. 1736 to 1813. So this guy figured this out hundreds of years ago. He just did the raw math and he was like, wait a second. If you have two things, there's going to be a place in the middle where it's not being pulled one direction or the other.
From Isaac Newton's math.
Yeah.
Yep.
Smart guy. All righty. Let me go back here really quick. So Diego, I know that you were asking me, like, wait, so if this is happening between the Earth and the sun, wouldn't the same thing be happening between the Earth and the moon?
Earth and the moon?
You're absolutely correct. So sun and Earth here could be substituted for any two large objects in space, any two objects in space. This could be Jupiter, and this could be one of Jupiter's moons. This could be Saturn and one of Saturn's moons. It could be Pluto and its moon, Charon. There's going to be the L1, 2, 3, 4, and 5 Lagrange points around those two objects.
And so when they go to the moon too, for the Artemis project, they're going to be looking for those points too.
Exactly. So this shows the Sun-Earth Lagrange points and the Earth-Moon Lagrange points. So here's your between Sun and Earth, 1, 2, 3, 4, 5. But also you can see around between the Sun and the Moon. So here's the L1 Lagrange point between the Sun and the Moon. The Earth and the Moon. I'm talking so fast today.
You're doing great.
And I'm making mistakes. And that
they can always
sometimes.
hit rewind on YouTube.
So I can watch me make mistakes again?
No, they can hit back home. If you're going too fast, you can always like.
That's right. So here's the Earth-Moon L1 point. And then past the moon, there's the L2. On the far side of the Earth from where the moon is, there's the L3 Lagrange point. There's Lagrange. And then 4 and 5 in the moon orbit around Earth. So, yeah, that's cool. As you were saying, the Artemis mission, as NASA sends humans back to the moon, I think that the plan is to leave a space station parked at the L4, L5 point, something like that. I'm not 100% certain.
They're still working things.
They're still working on the math.
Yeah.
I know that when the James Webb Space Telescope launches in the next year or two, I'm pretty sure it's at that L2 point that they plan on parking it. The Sun-Earth L2 Lagrange point is where the James Webb Space Telescope is going to be parked. Now, if you really want to go out and impress your friends and, really just show them that, hey, what did you do during quarantine? Oh, yeah, I played a lot of Call of Duty. Yeah, well, I learned about Lagrange points. So there you go. Let me tell you all about those. All right. Oh, someone's asking, what are the lines for? That's just to show the
alignment,
the alignment and the relation between the sun and the Earth and moon. Whoo!
This guy.
Good job, Joseph Louis Lagrange.
Lagrange.
Now, how does this look in our solar system? How can we use this to understand something that's happening in the natural world? Well, there's something called Trojan asteroids. These are asteroids belonging to one of two groups which orbit the sun at the same distance as Jupiter at the Lagrangian points ahead of and behind Jupiter in its orbit.
Whoa.
And
let that soak in.
Yeah, let's let that soak in. Earlier, we were looking at the asteroid belt. There's the asteroid belt, and then there's this smudge and this smudge here. And if you're looking, hey, Jupiter is right there. That looks like the L4 and L5 Lagrangian points that we just learned about. You're absolutely correct. Here, I put a lot of slides in here. Here's what that looks like in practice. So this is a lapse taken over, let's see what the range of time is here. So this is about a 10-year loop that we see from an 11-year loop from 2005 to 2016. And you see Mercury, Venus, Earth, Mars, and then there's Jupiter's orbit on the outside. And look at those turquoise asteroids just hanging out at that, in that kind of parking, that parking lot of space that we were looking at for the L4 and L5 Lagrange points. And they just kind of, they're just chilling there, dancing around a little bit. And then you'll see that there's some asteroids that kind of migrate, they travel, they go on vacation. They're like, well, here I am at the L4 point, now I'm going to go to the L5 point. And then from the L5 point, where's that 5 and 4? Honestly, I mix up. I know that the 4 and 5 points are the ones that travel ahead and behind on the orbit. I can't remember which one is which, but
in 3D space.
In my field, that doesn't matter too much. And then, so one will take a break and it'll go out to this third region over here on the far side of where Jupiter is, which you're thinking, isn't that about where the Sun-Jupiter L3 point would be? Yep. And then it comes back to the L4 and then L5 and then L3, and they dance around. I've looked at this for 2 days and it's mesmerizing. It's gorgeous. Galadriel's asking, what does Lagrange mean? Lagrange, so there's this dude, Joseph Louis Lagrange. Lagrange was his last name. And he's the one that figured out the math that, there would be points where the gravity is pretty much equal between two objects.
And I'm going to say hi to Kai. Hi, Kai.
Hi, Kai. Is the space station around L3? No, Kai, our International Space Station is not at a Lagrange point. The space station is orbiting the Earth much, much closer than any of the Lagrange points.
Every 90 minutes, going around.
Every 90 minutes. Alette is asking a super important question. Can you have earrings on in space? I would think big hoop or earrings that are very dangly. I would not wear those kinds of earrings in space. If you have a smaller stud or something like that, smaller earrings that aren't going to float around and get caught on stuff, I think that would be really cool and pretty to have on in space.
And,
Yeah.
and people throw things in space though too. So you're like, oh, here's this. It's easy to just throw things when you're on the space station.
Here you go, Diego. Huh.
And then I'm wearing a big hoop earring. It snags.
Ah! Yep.
I probably wouldn't recommend it.
Ooh, Sarah says the olden days sound like fun. Everyone discovers things every other week. Yes, Sarah, but there are more scientific discoveries happening per year right now than have happened than I would have to guess at any other point in history. Go ahead. I was going to say technological, and then I decided to change it to technology. Technology is moving so quickly. Advancements are happening so fast right now that the rate of discovery right now is incredible. Your phone, my phone is 3 years old, okay? And it's
old.
It's ancient.
Ancient technology.
Yeah. Whatever, if I buy a laptop next week, in a couple of years, it's going to be not completely obsolete, but definitely a little bit behind the times. You could have the kind of the same basic technology for hundreds of years back in the olden days. How long did it take to go from like the bow and arrow to the gun? Thousands of years. And then it took maybe a couple hundred years to go from the gun to like a really high-speed precision rocket. That's a really bad example. It took us over 10,000 years to figure out how to fly. The first instance of powered, controlled human flight was in the early 1900s. Less than 70 years later, we landed a man on the moon. Talk about the rate of advancement. Now, it's also been 50 years since we've been back, but we're fixing that. And the computers that they used to send men to the moon and land men on the moon and bring them back. There's more computing power in my mouse, I would have to guess, than there was in the computers. Okay, that's not absolutely true. But definitely more computing power in my phone than there was on the most advanced computer working at NASA at that time. And my phone is 1 billion times better than the ones 10 years ago. And the phones 10 years from now will be 1 billion times better than this one. I'm making up a big number, but the point is true.
Sure.
Okay. I really went off topic there. It is 2:10. I promised we were going to end precisely on time today, and I'm going to keep my word.
All right.
Let me go to this final slide here, everyone. Oh boy. I didn't skip so much this time. I want to give a deep and heartfelt thank you to everyone who's joined this class and every class that Diego and I have done in the past. We'll see you in about 20 minutes for our grand finale. Thanks, everyone.
Thank you.
Helmet up. One last time.